So good afternoon, ladies and gentlemen, and thank you, Alessandra, and thanks to all the colleagues for the opportunity of being here today. So I'm going to present a doctoral thesis work which will be coordinated jointly by my colleague Angelo Norati from the Internal Combustion Engine Group of the department, and by myself as a representative of the catalysis group in our department. And let me give you just a little bit of background first of all. What we have learned from the Alex Yetzeret's brilliant talk in the morning today is that internal combustion engines are actually here to stay for a while at least. However, a key challenge that needs to be solved to extend the lifetime of internal combustion engines is the reduction, the drastic reduction of their polluting emissions. This is a key challenge and actually requires a substantial enhancement of the existing catalytic technologies for the cleanup of engine emissions. Further to that, the hybridization of the vehicles will strongly also impact the emission levels. In particularly, the temperature levels will be affected, and also we can expect significantly more transient operation modes of the catalytic devices for the emission control. So, in essence, a change of paradigm is substantially needed. Luckily enough, however, also new tools are becoming available, and one of them is represented by the new additive manufacturing techniques which are being developed, which enable or at least promise an outstanding freedom in the design of novel cellular substrates for the catalytic devices that we can install on board of vehicles. And the goal of the thesis work that I'm presenting today is exactly to explore this freedom with the aim of designing, developing, testing, and assessing new cleanup catalytic devices based on these new enhanced cellular substrates. What we know from preliminary studies is that the transport properties associated with these open cell structures in terms of pressure drop, in terms of mass and heat transfer, can significantly outperform the conventional honeycomb monoliths which have been implemented already 40 years ago in the exhaust aftertreatment catalytic technologies. So what we will do essentially is to address both computationally and experimentally the study of these new cellular materials according to a multi-scale approach where we first investigate the geometry and the transport properties of these 3D printed cellular structures with different shells, shapes, cell shapes, different geometries at the micro scale level, and then we scale up these results to the simulation of the full-scale exhaust gas aftertreatment system under real working conditions. To meet this goal, we will combine the knowledge and the expertise of our two research groups. The internal combustion engines group has a well-established and well-recognized experience in the development of numerical tools for the simulation of non-reactive and reactive flows in combustion engines. Also addressing the coupling with the exhaust gas aftertreatment systems downstreams. And they are currently involved in three highly relevant European projects which are listed in this slide here. On the other side, our catalysis group has a recognized experience in the investigation of industrial catalytic processes, and particularly we have a long tradition in the investigation of catalytic processes for the abatement of polluting emissions, specifically in the area of automotive catalysis. And what is particularly interesting is that we are already collaborating intensively and very satisfactorily with the internal combustion engine group in the Thomson project, which is focused on the development of optimized cleanup technologies for passenger cars with mild hybridization. And we are also involved in two major projects dealing with the development of structured catalysts, which is also quite relevant for the topic of the doctoral thesis that we are discussing here. One of them is funded by the European Research Council and has to do with the application of structured catalysts to the intensification of catalytic processes in general. But we have also support from the Ministry of Education and Research in Italy for a related project which is focused specifically on the application of structured catalysts to the exhaust gas aftertreatment technologies. So here is the plan. What we are going to do is to start with the development of numerical strategies and approaches for the simulation of transport processes and reactive phenomena at the micro scale in innovative cellular substrates. In parallel, we'll also run an experimental multidisciplinary activity which would imply the 3D printing, additive manufacturing of different cellular structures with different geometrical characteristics, the catalytic activation of such structures by wash coating with a catalytic material. We will run measurements for the heat and mass transfer properties of these systems along with the pressure drop measurements. And we will, of course, also run at lab scale catalytic activity tests also under transient condition to fully characterize the performances of these systems. And the goal eventually is to scale up all of these results in order to develop optimized cellular substrates for advanced cleanup technologies and to achieve a model-based assessment considering also the latest protocols for vehicle test cycles. Thank you all for your kind attention.